Yes.
Okay, very good. Well, hello everyone. So the title of my talk has, of course, changed quite a bit since when I submitted the abstract. So now, today I'm going to tell you about superconducting triplet rim currents in a spin-textured ferromagnetic disk. Now, I'll tell you, of course, what these rim currents are, but the manuscript now for the work that I'm about to show you came out this morning on arXiv, so you can refer to that for future. Right. So I work at Leiden University. Actually, I work. The result I'm going to show you is a joint effort, of course, with Remco Fermin, who just gave a nice talk about strontium glutamate, and in Leiden we also have Jan Arts, who was also my PhD supervisor, and he's been involved in this project since very early days. And Dion was our master student, and we also have been enjoying theoretical inputs from Mikhail Silayev. So the works I'm going to show you, part of it is, of course, about the experiments in Leiden, and part is from his theoretical efforts. So since this is maybe the first talk on triplet superconductivity, maybe I should just say a few words. Well, you now know that we have, of course, singlet pairing, but we can also have triplet Cooper pairs. Now, if you have a triplet pairing, you have a spin of 1, but you could have 3 different spin projections. You can have a spin projection of +1, -1, and 0. So where do we find this type of triplet pairing? Well, that depends on what type of triplet you're looking for. See, there are by now quite a few materials. It used to be very few, but now we know, let's say, several unconventional superconductors which have odd parity. So here we have even spin, but odd momentum, so it's P wave or S wave, and even frequency. So examples of this, of course, the most famous one is helium-3 and uranium-platinum-3. And for quite some time, let's say over a decade, strontium glutamate was supposed to belong to this category, but as Remco pointed out, that is no longer the case. So, yeah, but we're still finding new triplet superconductors. Now, you could also have odd frequency, even momentum triplet pairing. This, however, well, for whatever reason, we haven't seen examples of this pairing naturally in materials. But what you can do is that you could engineer superconductor ferromagnet hybrids to generate this type of odd frequency triplet. And one advantage of these odd frequency triplets is the fact that because they have even parity, and let's say they have, especially since they are S-wave, they're robust to non-magnetic impurities. So they're actually quite immune to inelastic scattering, which would not be the case for P-wave and S-wave symmetries, for instance. So because they're so robust, they can also survive in diffused ferromagnets such as cobalt and permalloy and so on. Okay, so how do we observe these triplets? Well, if you just have a superconductor and a ferromagnet interface, and if there is nothing special happening, what you have is that you convert some of the singlet Cooper pairs into triplets. But these are M0 triplets. So this is a triplet component with no spin projection. And even though this is triplet, still we have both spin up and down, and this type of triplet is actually very short-lived. It can't penetrate the ferromagnet for more than a few nanometers. Now, in case of cobalt, which I'll be showing you later, this would be the decay length be at most about 5 nanometers. Now, suppose that you have a superconductor ferromagnet interface, but here you have an intermediate layer where the magnetization is non-collinear, or let's say it's perpendicular to the magnetization of your, the main ferromagnet. In this case, what happens first is that we still, of course, generate these M0 triplets, but now the M0 triplets is defined with respect to the spin quantization axis, which is defined along X. So because the exchange field of the intermediate layer, this thin layer, is along the X, your triplet group pairs will also have a zero spin projection along X, which means that they will have a spin projection in the YZ plane. And therefore, when they go to the next ferromagnet, there they can actually turn into plus or minus one triplets, so equal spin triplets. And these type of correlations are long range, and they can exceed, they can exceed up to hundreds or even almost close to a micron in ferromagnets, even half metals. Okay, well, this is the let's say the usual way of generating these long-range triplets. It's based on what we call this, let's say, magnetically non-collinear Josephson junctions. Now, and this is by far the most popular device configuration for a triplet supercurrents. And well, as it turns out, it's not so easy to get this non-collinearity between these ferromagnetic layers, because you'll need at least 3 in this case. And in order to get 3 non-collinear ferromagnetic layers, that's actually you need to overcome the coupling between these layers. Now, exchange coupling we can remedy easily using a thin buffer layer, let's say copper or something. But the dipole fields coming from these ferromagnets are harder to disentangle, because if you can imagine that if you put 2 magnetic bars on top of each other, they never want to be perpendicular with each other. They always tend to be either parallel or anti-parallel. And it's kind of the same story here, but different groups, of course, develop different techniques to overcome this. So here is a paper by Norman Berg's group, where they use these cobalt, ruthenium, cobalt layers, which is a synthetic antiferromagnet, which does a great job in reducing the stray fields, so they can control the magnetization of the other layers. And here's another example from the Cambridge group. This is where back then they used holmium, which cobalt holmium trilayer, which ends up having giving you some non-collinearity between the spiral magnetization of holmium and the cobalt, which would be in play. Well, when I started working on triple superconductors, I went in a different direction. My approach was to use a ferromagnetic vortex to manage these stray fields. And this is an example of this. So here I'm still using, let's say, the tri-layer. We have the nickel, we have the cobalt, and then back again nickel. But here I designed the Josephson junction in a way that the cobalt layer will have a vortex magnetization. And magnetic vortices are extremely controllable, they're stable, and they do a great job in minimizing stray fields. As you can see here, the cobalt has this vortex magnetization, but the nickel layer on top has a completely independent spin texture. And using this configuration, you also see that you get quite a lot of non-collinearity, where your weak link is because the nickel wants to be parallel to the trench, which defines our junction, while the cobalt is actually perpendicular to it. But of course, this I'm not going to talk too much about this. I want to actually talk about a completely different system, which is, well, here's the thing. Until now, let's say the vast majority of experiments on triple superconductivity has been done using these magnetic trilayers, or these non-collinear magnetic layers. But at the same time, there is, let's say, numerous theoretical proposals which suggest that the spin texture of a single ferromagnet itself could generate these long-range triplets. Now, by spin texture, I mean either you have a, let's say, a ferromagnetic vortex, or if you have a domain wall. So there are actually, these are just some examples I could find last minute, but there are actually plenty of examples where a domain wall, the block domain wall, nail domain wall, and so on, are, let's say, proposed to be, or let's say, expected to generate long-range triplets. But when it comes to the experiment, well, with the exception of what the results that I'm going to show you today, actually there's only one other work which came out recently. This is, of course, also Jason Robinson is also on this paper. This is the only paper that actually you will find where there's a clear indication that spin texture, or let's say the magnetic domain structure, are generating the long-range triplets. So this is quite a bit of a puzzle, because if magnetic domains or any type of homogeneity can generate long-range triplets, then it's a bit puzzling that we don't see it in experiments. And so that, however, so is something that we can actually want to look into here. And we're going to actually continue with the same vortex magnetization. So here, this is the same, let's say, in a way similar to the system I just showed you, but there is one fundamental difference, and that is the fact that there is no secondary ferromagnetic layer. So here, we only have the niobium and cobalt, only a bilayer. And we formed our junction, of course, by focused ion beam milling. So first we structured into a disk. It's a micron to 2 micron disk, depending on what we want to do. And we defined this weak link by removing the top niobium layer, also using focused ion beam. And this way we can get somewhere between, let's say, somewhere around 20 nanometer gap, or 20 nanometer cobalt weak link to be our junction. And this 20 nanometer, of course, is too large to, it's large enough to filter any single transport, but it's also not too large, so you can actually get a decent critical current and study it. Right, so what do we see? Well, here I'm showing you just some basic transport characteristics. Well, on the right, you see these Shapiro steps, so we definitely have proximized Josephson junctions. And on the left, you see the resistance as a function of temperature. And you'll notice that there are two transitions. The first one, of course, is just for the disk. You will have it even if there is no trench, no weak link. So this is the electrodes transition. And the one that this plateau, which eventually goes to 0, corresponds to the 20 nanometer cobalt layer. But now here's the interesting part. See, If we get rid of this spin texture, if we suppose we use the exact same method and same methods and same deposition parameters and everything, and same dimensions, but instead of a disk which has a vortex magnetization, we make a straight bar like this one, where the shape anisotropy forces the magnetization to be uniform. When we make samples like this, you'll see that we see no sign of proximity effect, even though both junctions have the same normal state resistance. So even though the weaklings are exactly give you a resistance of about 200 milliohm, these junctions don't go superconducting. So it already tells you that what we're dealing with here is that is the generation of long-lived triplets using spin texture. And we don't have any supercurrents once the spin texture is removed. But okay, so now we're going to look at what the interference patterns of these junctions look like. I mean, in a normal superconducting Josephson junction, you will see this Fraunhofer pattern, or at least some version of it. But and this corresponds to a uniform distribution of supercurrents, supercurrent density across your junction. But what we see consistently, and this is now over 20 samples that we've measured, is a very distinct and striking split pattern. So here, you see that already this is quite different. We don't have the decay of critical current, and also all the lobes have the same width. So it's very clear that this is not a Fraunhofer, and it's a very strong two-channel behavior. It means that we need to have at least two transport channels. But what we could do better, you could actually do an inverse Fourier transform of this pattern to reconstruct the critical current density across your junction. And Remco did a great job doing this, and here is what we found. So we found that regardless of, so here what I'm showing you is two different Josephson junctions. One has a diameter of 1.05 micrometer, and the other one is 1.6 microns. And in both cases, we see that we find the supercurrents to be extremely localized at the edges of the junction. And this type of behavior you would expect in something where we have, let's say, in some material where we have, either there's some topology or there's a special band structure that leads to edge space. But for something like cobalt, that is just not possible. So this is not, just to be clear, we're clearly not dealing with any kind of edge currents or edge space which emerge from the electronic bands. Here what we're dealing with is a direct result of the magnetic texture, and I'll tell you the rest in a moment. Now, here's another experiment that actually is quite interesting. So what we're doing is that we're using an in-plane field to alter the spin texture of this disk. And we're going to look at what happens to the interference patterns. So if there's no in-plane magnetic fields, you see this split pattern. But if we apply only a tiny amount of in-plane field, let's say only 10 millitesla, then suddenly your critical current actually goes to zero. And here where you had maximum at zero field, now suddenly you have minimum at zero field. And this happens regardless of which way you sweep the outer plane field. So if this looks like, let's say, a standard split pattern, this would be the 0 pi square. And now if we go a little bit further, so we push the vortex to the side by applying the 40 millitesla in plane field, then suddenly the critical current re-emerges. And one thing you'll notice is that now the middle lobe is actually wider than what it used to be. Now, this pattern, especially this one, is a little bit, it's not very continuous. There's some jumps here and there, so we can't really do a very good Fourier transform. But what seems to be happening is that we're actually changing the distribution of supercurrents. So we start with the 2-channel, it seems to then go to a 0 pi split, and then here it looks like we're actually ending up with 3 transport channels. Well, now before I go any further, I should also mention something about what happens if we don't cut completely through this niobium layer. So suppose if there is still a little residue of niobium left. In this case, of course, your transport will be dominated by singlet Cooper curves, and we always end up with the standard Fraunhofer pattern. So you see the middle lobe is twice as large, and we also don't see any dependence on in-plane fields. So even if we apply up to a Tesla, this critical current hardly ever changes. You still retain a finite amount of critical current. So the fact that the supercurrent, its amplitude, its phase, and distribution is so strongly affected by spin temperature are all indications of the fact that this is a phenomenon that actually has to do with the interaction between triplet Cooper pairs, long-range triplet Cooper pairs, and the spin texture. So it actually took us quite a while to figure out what is happening here. At first, we thought, well, maybe this is the long-range triplets we see as a result of this model that was proposed by Kalenkov and Petroshev. But this can't explain the 2-channel behavior. And also the length scales don't quite match. And at this point, then finally, we started collaborating with Mikhail. And here, actually, a breakthrough was that he pointed out that if we have a vortex spin texture, this is actually equivalent to a uniform magnetization, but with an intrinsic but inhomogeneous spin orbit coupling term. Now, of course, there's not going to go through all the mathematical formalism, but what we learned is that this vortex spin texture, you could actually map that into an effective spin orbit coupling, and this effective spin orbit coupling leads to an equilibrium spin current. Now, maybe I can show you better here. So what I'm showing you here is basically the magnetization of the ferromagnet, and then now you're looking at the Cooper pairs in the superconducting layer, so at the interface. Now, if magnetization is uniform, the Cooper pairs will always will only have let's say short-range triplets which have whose spins are always going to be perpendicular to the exchange field. And here, well, nothing exciting happens. You just have triplets, but their spin is always perpendicular to the magnetization. But what happens if you have now rotating, let's say if you have this spin texture? Well, here again, the Cooper pairs also need to rotate their spin plane. So these triplets locally at each point need to have their spin plane perpendicular to the local magnetization, and this rotation of the spin plane of these M0 triplets leads to an effective equilibrium spin current. Now, this spin current has 2 components. Of course, it's in space and also in spin space. In this case, the spin current would actually have a z component, but will follow the magnetization texture of the disk. Now, so then the question is, what happens when this equilibrium spin current reaches the vacuum boundary? So suppose you hit the edge of the disk, and at that point, what happens is that this adiabatic approximation we have it falls apart. So here we can't have a spin current. 5 minutes. Okay, that's enough. So here what happens is that at the interface, of course, your spin needs to be conserved. So we have a spin current that's carried by these M0 triplets. How do you cancel that out? Well, one way that to do it is, of course, to convert this into equal spin triplets in the opposite direction. So, of course, Mikhail has done a lot of calculations, and he does a great job in the paper talking about this. But so the bottom line here is that what we have is that the process, just to recap, we have a spin texture and a spin texture which leads to an equilibrium spin current in the M0 triplet condensate. And this M0 triplet current, the current carried by these M0 triplets, when it hits the interface with that boundary, it gets reflected as long-range triplet currents. And here is basically just the final thing. What Mikhail is doing here is, he's doing linearized musical calculations. And here's the result. So the color scale would be the amplitude of the long-range triplets. Now, when the magnetization is uniform, let's say when we magnetize this, there is no long-range triplets, regardless of what the geometry is. But if here's the other exchange, this is when we have a vortex pattern that is perfectly symmetric, but we have imperfect edges. So here we put these notches in the structure to create these imperfect edges. And here you see again long-range triplets, two long-range triplet channels appearing at the edges. And now, even if we have, which is where it's really interesting, even if you have perfectly pristine boundaries with atomically smooth edges, if your vortex structure is not completely symmetric, then you also end up with long-range triplets. So, I must, however, say that this is a two-dimensional model, and we're kind of not really simulating what happens exactly at the trench. We're just looking at, let's say, a bilayer, and we're looking at these what happens at these edges. So to summarize, well, we know now that we can generate long-range triplets using spin texture alone, and we also found that the superconductor, the vacuum boundary conditions play a crucial role here. And well, there's still, however, plenty of questions. For once, is a question of what determines the width of these rim current channels. Well, since this is turns out to be about 8 nanometer, and also the spin diffusion length of cobalt is also in that range, it may be that this is limited by the spin diffusion length of cobalt. But of course, we need more data to verify this. And here is again is the ID code for our manuscript. Okay, and with that, I'd like to thank you. I see somebody in the front. Hi.
Hi, can I ask a question?
Yes, sure.
So, you show this Fraunhofer pattern, a modified Fraunhofer pattern, and I wanted to ask, can you explain the shape? Why is it spiky shaped?
Which one?
Well, the ones, maybe you go on. Oh yeah, this.
Well, okay. So you mean this shape?
The shape of the IC versus H, yeah.
Alright, so well, there's two things. First of all, I tend to be a bit careful. I wouldn't call this a Fraunhofer pattern because this is a double slit pattern.
Yeah.
But let's say that's one. But I think your question is why we have this sawtooth-like oscillation.
Yeah.
That is actually a good question. We don't No, this is also, well, it could be a result of current phase relation, and this also, of course, I think Sasha Golubov could tell you all about it. I think in the long junctions, in short junctions, of course, this I can't remember which one. I think it's also kind of characteristic of long junctions that you get this linear up and down shape that you get. But that's a good question. I don't fully know, but it's either the current phase relation or it has to do with the length of our junction.
Okay, question. Can you measure, can you detect spin currents in principle with your elements?
And that's I've been wondering that. Okay, so the spin current, the spin currents that we see here, at least let's say in principle, this is also being predicted to also exist in the normal state. So there's paper by Sebastian Berger and Kaveh, and also there's more paper. I think there's a few by Aridus and Bokova, where so the spin current, this equilibrium spin current, is always present, even in the normal state. But we only see it in the superconducting state because that's where we can do all this interferometry and inverse Fourier transform and so on to see it. But I'm not really sure if a good experiment would be to look at to inject some spin current into this and see how that gets distributed. But